In this experiment, we're going to look at fundamental constants of physics as determined by the properties of gases. And we'll do that with some very simple apparatus. We just have a balance here and used a can of what formerly had been coffee that will fill with different gases and then actually measure the mass of that gas in that container. And that measurement will tell us how many atoms or molecules are inside that volume. Then we'll also come back and measure how the temperature of the gas alters the pressure, and through the ideal gas law, we'll use that to determine one of the fundamental constants of physics, the Boltzmann constant. So the first thing we'll do is balance this container, which currently just has air in it. It had been opened and then closed again. You can see the balance reads very close to 0. We've removed the pan from the balance so that it comes out roughly balanced when we add this coffee can to it. The small gram scale, which is on the front side of the balance, as you can see here, reads 4.5 grams at the present time. And that's the one that we'll have to trim when we change what is inside that container. So I'm going to go over, take that container off, go to the other room where we have a tank of helium. I'm going to fill that container with helium gas and then bring it back, and we're going to measure its mass. So the first thing I'll do is take it off, and we'll be back in a moment. So now I'm back with a container. I've put some helium inside it. It's pretty easy to do because this seals, and you open this up and flow helium up in here. It rises up and fills the container until it flows out. You snap that back on there, which I'll show you. I'll go back over and we'll take the camera over there later. So to get this to fit, I have to turn this on its side. It goes this way. And we'll stick it on there. And you notice that it's not balanced anymore. It's a little too heavy. So we're at 4.5, and I'm just going to move this back until it balances. Looks like it's about 2.1 right now. So just to show you what happens, I'll take this off and I'll turn this upside down. I should feel a flow of helium when I open it up, and I do. I should breathe that. So you can actually hear it, and then I'll do this. I'll put this back on here. Now that's got nitrogen in it, mostly air, and it's too heavy. The same amount, you can see it. So we'll go back over here. Should come out about 4.5, which is where we started. Looks like it's pretty consistent, about 4.6. So that's air. We put helium in, and it had less mass in it. The lift, when you think of helium as lifting something because of the displaced air, in the ideas of Archimedes, it works. That's why balloons lift. In this case, the volume is the same. So although I replaced what was inside with air, the lift which was provided, which is the displaced volume of the air surrounding this, is the same in both cases. So the two different measurements is actually the difference in the mass of the air that's in there now and the helium that was in there when we did this experiment. So just so that you'll see that this is repeatable, I've filled the container again with helium. I'm going to put it back on here. You can see it's lighter now than it was, and I'll go back over here to the setting we found before, about 2.1 or so. A little heavier this time. So it comes out about 2 point, maybe 4 this time. Pretty close to the same. So now just to demonstrate, I hope this will work, I'm going to take this top off and take a deep breath of this. It's supposed to be helium, remember? So it's going to rise up. It'll stay inside the container, but until it comes upside down. Now, see, that's what happens. Helium gas changes the speed of sound, and just a little breath of it, and we get a change in the frequency. So helium and air have different masses. So now it's all the same, except this time I put nitrogen in here. So instead of air, it's N2. And let's see what we have. Put that on here. What do we have here? We'll go over here. So what do we have for N2? Not 4.5 anymore. About 4.4 maybe. Close to that of air, which it should be because air is mostly nitrogen. A little bit less. So I just wanted to show you how we fill the container with helium because it's an interesting trick and it actually makes the experiment work easily. So this is just a standard discarded coffee can. It's got a seal on the inside, and when you put this top on there and snap it in place, it will hold the gas inside for quite a while. So all I really have to do is get gas in there and get the top on it, and you can actually do that with a flow of gas from a compressed gas cylinder. This is helium, laboratory grade at high pressure. When I open this valve, it comes up and tells me I've got 8,000 kilopascals of pressure inside this tank. I have a regulator which reduces the pressure so that over here on the output side it's about 1,000 kilopascals. And then when I open this small valve, the gas will flow out through this hose. It's normally connected to an instrument in the lab, but I've just borrowed it for this. So when I open that up, you can hear the helium. And then we'll just put it up inside here like that. There's a little lock, I can probably get it to work here. So we'll just open this up. It's filling that can up. And just kind of pull it over like that. Try to hold it level. And fill it up with helium. Snaps that. So now I've got a can of helium, and that's what we measured when we weighed the helium gas inside the can. So to measure the volume of the container so that we'll know how much gas we had when we weighed it, I've got a beaker here that's graduated pretty accurately, and I filled it to the 1 liter mark, the 1,000 milliliter mark, 1,000 cubic centimeters at this point. I'm just going to pour that in here. Comes up about halfway, so I'll go get some more water and we'll do it again. And we're ready to do the 2nd liter here. Pour that in. Pretty sure it won't flow. Not quite at the top, so we'll need some more. Now the beaker is conveniently graduated. It's full at 1,000 milliliters, but it also tells me how much I've taken out as the level goes down. So we'll just add until it tops off at the top of this. Try not to overflow. Make a mess here. That's pretty close. You can see we're down at just a shade more than 300 milliliters additional to the 2 liters that was already in there. Now we have a top, and the top goes on there like that, and it seals on that inner edge. So I'd actually like to add some more water to measure the volume inside here, and try to do that without, not quite level here, but we'll get it pretty close. So allowing for the top, we're now down 400. So we've got 2.4 liters of volume in this container that contained the helium and the nitrogen that we measured on the balance. So we're going to do an experiment today to look at how the pressure changes in an enclosed volume when we decrease the size of that volume while keeping the number of atoms or molecules in the volume constant. So this demonstration apparatus will let us measure that to enough precision to be able to show that it holds up as one of the fundamental ideal gas laws. So we're looking at a gauge which measures pressure. It's a mechanical gauge. It actually reads pressure by force. And there's a spring here. This C-shaped object is a spring which will move in response to pressure, and then it's amplified by a little gearing mechanism so that that needle is calibrated to read in pounds per square inch. This chamber is open right now to the atmosphere at this side. And then I have a standard little syringe up here, which is calibrated in cubic centimeters, so that's 5, 10, 15, 20, 25, 30, and now all the way out at 35 cubic centimeters in the volume here. And we're going to change the volume of that by depressing this plunger while we look at how that pressure changes. The current pressure is atmospheric pressure, which reads on that gauge there at about 15 pounds per square inch. And we can actually measure the temperature. You may be able to see this with this infrared thermometer that looks at the black body radiation from the plastic that's holding that chamber, the gas in that chamber enclosed. So it reads about 74 Fahrenheit at this point. That temperature will stay about the same as we do this because this whole apparatus is in equilibrium with the room. Now we'll start with atmospheric pressure. This is open. The gauge is attached to that fitting through a small volume mechanism which actuates the spring that measures the pressure inside that chamber. So I'm just going to connect this to that by depressing this fitting and sticking this little thing in there like that. It should there. So now we're measuring the pressure that's over here in this volume. And I'm just going to decrease that volume. We start with 35, and that's 30. And then 25, and 20, and 15, and one more step. I'm going to go down here to 10 cubic centimeters. And then gradually open it up to 15, 20, 25, and 30. Letting the force of the gas actually push it out to 30 here. Now we're going to do a different experiment using the same gauge and the same idea, but a fixed volume. This is a metal sphere. It's 10 centimeters in diameter, so you can calculate the volume of gas in that sphere. And it's connected to the same kind of hosing that we had before with the volume experiment. But now the volume here is going to be fixed, and I'm going to change the temperature in this volume. I'm going to do that with a hot air gun. This is a device that's used for soldering, so it can get quite hot. It can melt metal. We won't use it that hot, but I want to see how the pressure changes when this fixed volume is heated. So I've attached the hose to the pressure gauge. The metal sphere is full of atmospheric pressure air at what amounts to room temperature here in my lab, and you can actually measure that with this infrared thermometer if you can see it, it might not be in focus, but it reads 76.5 Fahrenheit, or maybe 76. It kind of varies a little bit. And then I'm going to turn on the hot air gun. And you can see the temperature here is the temperature of the air coming out of that gun. And it's pretty warm. And the end of the gun is not warm, but the air itself that's coming out is very hot. So I'm going to put that gun on the metal sphere here for a few minutes, and we're going to heat it up. So I've been heating this for a while now, and with air temperature of 412 Celsius, the metal sphere is hot, but not as hot as the air. You can see the pressure has increased because the temperature of the gas in this sphere has increased. So let's see if we can get a measurement of the temperature in that sphere. It'll hold for a few seconds while I set this aside. Measure that. So the sphere is now at 108, 111, 112. It depends on where we measure it. 110. Let's call it 109 Fahrenheit. The highest measurement we got was 112. And the pressure has increased, as you can see on the gauge. So we made two fundamental measurements with this simple device. We looked at how the volume affects the pressure. Same amount of gas in this volume, but we decreased the volume, so we increased the density of molecules per unit volume, and that led to a pressure increase. And then we took this chamber, which is still a little warm from the experiment that we just did. We heated up a fixed volume of gas, and that also increased the pressure. But now the density is the same. We have the same number of molecules per cubic centimeter in this 10 centimeter sphere, but the temperature is increased. So the idea here is that the temperature measures the energy that is in those gas molecules. And we have increased the energy density by putting energy into the sphere with the hot air gun. We increased the energy density too by decreasing the volume, so that the same number of molecules were crowded into a smaller volume, increased the energy density. The pressure is really a measure of energy density in the gas.